This is part 1 of my do-it-yourself, 3D printed, scale Bally Fathom pinball machine. The topic of this video is milling the playfield from a plywood board. Okay. This is not a Fathom. This is my previous pinball project, a replica of the Williams Space Shuttle. It's time for me to build a new machine. I did some research on the internet and came across a site that lists the best pinball machines of the 80s. Since my current technical capabilities are limited, it had to be a model from the early 80s. I came across the Fathom and Centaur from Bally. What appealed to me about this one are the drop targets which are lined up one after the other. I finally decided on the Fathom. Quote from the website. For a game from the early 1980s, this table is packed with features like inline drops and a multi-ball. The sound effects and announcements were also quite engaging and innovative for the time. One of the best graphics packages ever, helping to make Fathom one of the best pinball machines of the 80s. I started looking for documents about the machine and I ended up on the Internet Pinball Database site. I was extremely lucky that a playfield plan for the Fathom is available there. This makes the reconstruction much easier and ensures that the proportions will be correct when scaled down to a playfield size of 50 by 100 centimeters. For this project I took a different approach. Instead of using a blueprint to transfer the dimensions to the playfield and milling all the holes manually using templates, as shown here, I built a mostly printed CNC machine and milled the playing field automatically. As it turned out, this wasn't as beneficial as I thought. Regardless of whether it is milled by hand or automatically, the plan must be adjusted to the correct size. The playing field will be 500 by 1000 millimeters. I use the vector graphics program named Inkscape for this. I create a frame exactly as big as the playfield will be and place it directly above the document. This helps to position the downloaded blueprint better. Now the previously downloaded blueprint is imported and roughly adjusted to the required size. As it turned out, the blueprint was a bit distorted and also a bit twisted. The plan had to be aligned with the frame. In order to align the construction plan correctly, a circular area was inserted which has the dimensions of the ball. With this, the construction plan can be aligned so that the ball exit channel has the correct width. There was a lot of fine-tuning to do, a pretty fiddly job. Now a rectangle was inserted to adjust the bottom arch distance. I check everything again. Then I remove the circular area and the rectangle. Now I export the document as a PNG graphic. It will now have the exact dimensions required. I open the exported file to check it. This PNG graphic is needed in the next step. I save the work under a different name, remove the blueprint and import the PNG file I just created and position it exactly above the document. It is necessary to define at least 3 levels. One for the top and one for the bottom of the playfield and one for the blueprint. The parts which are milled or drilled from above and below must be inserted in the corresponding level. The frame which is already inserted for the blueprint is now copied to the other 2 levels. This is necessary so that the edge of the playing field is visible in the milling program. I have prepared vector graphics for the individual assembly types. These graphics must now be inserted and aligned individually at the appropriate location. Of course, it must also be inserted on the correct level and, if necessary, moved to the correct one, as here. The transparency of the assembly graphic is increased so that the blueprint can be seen through it. Now the drop target assembly is precisely aligned. This procedure must now be repeated for all assemblies. The inline drop target is inserted here. The gray area defines the space required by the assembly under the playfield, the green holes and red blind holes. The blue lines are for alignment. Now the 6-drop target vector graphic is inserted. The procedure is the same as for the drop targets before. I'll now continue with the arrows. I left them in the design of the Space Shuttle pinball machine because I like this design better than the Fathoms. These are copied and inserted and aligned at the appropriate places. Now the bumper vector graphics are inserted and aligned. All assemblies graphics must now be moved to the correct level. Now the graphics for the flipper axis position are inserted. Unfortunately, the blueprint is distorted, so I have to determine the position intuitively. The flipper distance of 178 mm results from the scaling. The vector graphics for the flipper assembly are inserted. 2 solenoids and a leaf spring switch are required per flipper. The graphic contains all 4 possible positions for these. The blue arrows correspond to the direction of rotation of the flipper. The graphics must be aligned so that 2 solenoids and a leaf spring switch do not overlap with other assemblies, lamps or sensors. The parts of the graphics that are not required must be removed. The red dots correspond to the holes needed to attach the pinball assemblies to the playfield. The third flipper is now inserted. Since there is not enough space for a 90 degrees arrangement of the solenoids, they are arranged one behind the other. As before, any graphic parts that are not required must be deleted. I copy the kickout assembly graphic. This is inserted and aligned in the appropriate places. The red area represents the space required under the playfield, the blue the required hole. Here too I remove the unnecessary graphic components. As with the assemblies before, I proceed with the slingshot in the same way. And now I do the same thing with the stand-up target. Since I did not delete the unnecessary graphic parts in some assemblies at the beginning, I am now doing this. Now the lane guides are inserted and the usual procedure is followed. The red dots correspond to the required holes. Now the holes for the lamps are inserted. The blue area corresponds to the hole and the cyan area to a blind hole. The blind hole is needed because the bulb socket thickens towards the bottom. In some places the holes for the lamps have to be aligned so that they do not overlap with other holes. I create a circular area for the lamps and sensors and copy and paste it in all the necessary places. I also change the size of the circular area accordingly. Here I notice that the blueprint differs from the real Fathom playfield. I check this using pictures that I downloaded from the internet beforehand. I insert these lamps according to the pictures. After all the lamps and sensors have been inserted, I align them horizontally and vertically if necessary using a graphic programs tool. Now I continue with the playfield posts. As before, the graphics are inserted, configured to be transparent and inserted and adjusted in all necessary places. I forgot 4 holes for the lane sensors before, which I am now adding. To be on the safe side, I check whether others are missing. I'll continue with the rail posts. The red dot on the posts corresponds to the hole required. The posts must be inserted at the level that corresponds to the top of the playfield. The rail posts will later hold the rail that defines the lane path. The top and bottom sides are milled and drilled one after the other. Therefore, I add labels that defines the level in the graphics program. The bottom of the playfield has to be mirrored, so I also mirror the label. Now I check whether all assemblies, drillings and holes are inserted on the correct level. This is very easy to do by fading the individual levels in and out. With the slingshots I also remove unnecessary graphic parts that are not needed for milling and drilling. To keep the video shorter, from here on only the bottom side is shown. Since all assemblies, holes and drill holes have been successfully created, the graphics, top and bottom, must be separated from each other in order to be able to import them individually into the CNC program. Therefore, I save them under an appropriate name. The entire graphic for the bottom side must be mirrored, rotated 90 degrees and saved as a DXF file so that it is displayed correctly in my CNC program. I use Estlcam as a CNC machining program. I open the previously saved file with it. Here I set the 0 point. I start to configure the drill holes. I defined a 2 mm drill in the CNC program, activated it and selected drilling. Now all the holes have to be configured. After the drilling holes, I will configure the holes for the lamps, sensors, bumper and kick-out hole. To do this, I switch to a 6 mm milling head. I now select the cutout function in the CNC program and use it to mark a group of lamps. I select these and define the milling depth as 19 mm, since my playfield is 18 mm thick. I also configure the complete cutout function. Here I switched to a 4mm milling head to configure the drop targets. I start with the blind hole, which should be 13.5mm deep. Then I configure the holes for the individual drop targets, which should again be milled 19mm deep. Now I configure the holes for the lamp sockets. To do this, I switch back to the 6mm milling head. First I configure the entire hole, then the blind hole with a depth of 7mm. Here is the end result after all drilling and milling operations have been configured and some cleanups have been carried out, such as removing irrelevant rectangles. I started the CNC machining simulation to check whether all milling operations were carried out correctly. Since the simulation was successful, the next step is to produce the playfield with my CNC milling machine. First I place the sacrificial plate on the CNC machine, then I take the plywood plate that will be machined and attach it. Then comes the fiddly work of aligning the plates precisely on the machine and setting the 0 point. I fix the plywood panel in the CNC machine. Now I adjust the level of the milling head. I do this like with a 3D printer with a thicker paper and slowly move the milling cutter down until the paper can no longer be easily pushed back and forth. I zero the X and Z axes by letting them touch the end. Since my CNC machine is very simple, this is the quickest way to do it. Now I have to make sure that the plywood panel is 100% parallel to the X-axis. To do this, I measure the distance between the panel and the milling head at various points using a sliding gauge. Here I have to move the plywood panel slightly. I loosen the fastening of the plywood panel and tap it into position with a hammer. Then I fasten the plywood panel again. Finally, I aligned the plywood and adjusted the CNC machine. The next step is milling. Well, it started with a big failure. Although I had already milled a lot with this CNC machine, it failed right from the start. Since the groove that was accidentally milled did not go through the plywood, I decided to continue. I had to remove the suction pipe from the CNC machine because otherwise the work area for the necessary milling would have been too small. I therefore do the suction manually with the vacuum cleaner. Some holes were milled without any problems. I assume that by removing the suction pipe I tightened some of the screws on the milling carriage too much, which affected the milling carriage's ability to move up. Unfortunately, I didn't fix it right away, so it happened again. Nevertheless, I decided to continue with this playfield in order to test the entire milling process. Of course, after each failure I set the 0 points of the CNC machine. I also solved the problem with the milling carriage. Milling the holes took about 2.5 hours. Because my stepper motors skipped steps, the playfield was anyway unusable. I had an offset of 1.5 mm between the first and last hole. Therefore I didn't mill the holes for the drop targets and drill holes. The result can be seen here. Manually vacuuming the dust was also very tiring. So I had to take care of the CNC milling machine first. After I fitted the CNC machine with a dust extractor and solved the problem with the stepper motors, I started with a new sheet of plywood. At the beginning everything looked good. This time my cheap milling machine started to have a problem with its rotary wheel, it just stopped. Luckily, I was able to stop the milling program immediately and there was no damage to the playfield or CNC machine. The complete milling with the 6mm cutter took 2.5 hours. Unfortunately, the cheap milling machine will cause problems again. Here the last hole is milled with the 6mm cutter. Then I clamped the 4mm cutter into the milling machine and continued milling. After all the holes had been milled with the 4mm milling head, I replaced it with a 1.5mm drill and drilled the required holes. After all the holes on the bottom of the playfield were drilled, I turned it over and drilled the holes on the top. After everything was milled and drilled, I deburred the holes with sandpaper. Milling this one playfield took almost 2 days. In addition to the long milling and drilling time of around 4 hours, there were many more hours of setting up and fine-tuning the CNC milling machine before each work step. This is the bottom of the playfield, and this is the top. Finally, I can move on to the next step. Here I mount the playfield on my work frame. This makes it possible to rotate the playfield 360 degrees and makes working much easier. The work frame can also be set to a gradient of around 7 degrees. This makes it possible to play pinball test games during the construction phase. I check whether the assemblies fit into the holes provided. Unfortunately, I milled the holes too small for the 6 and 3 in-line drop target assemblies. The targets don't have enough play in the hole and might get stuck. So I have to file the holes a little bigger. It's very laborious work. My conclusion in the meantime, compared to manual milling using templates, milling with a CNC machine was more labor-intensive and prone to errors. Likewise, when milling manually, all assemblies, lamps, etc. can be immediately inserted into the milled hole. If this is too small, the template can be adjusted immediately and the hole can simply be enlarged. The playing field also had to be milled with the CNC machine in one operation, which forced me to mill all the sensor and lamp holes. However, it is better not to mill these straight away, as this allows you to test the pinball machine and make small changes, and the sensors and lamps can still be adapted to these changes. The holes are large enough for this drop target. The same goes for the slingshot. The holes are big enough. With this one I also have to file the holes bigger. And unfortunately here too. So that this assembly can be inserted into the hole, I had to adjust my work frame a little to create enough space. I then checked all the lamps and sensors and, if necessary, enlarged the hole a little. My cheap milling machine had another problem that I didn't film. The collet somehow came loose and the milling cutter slipped out of it and milled these holes much too deep. I therefore had to insert inlays to close the holes and mill them again. To make the surface 100% even and smooth again, I fill them with filler. After the filler had hardened, I sanded everything off and broke off any overhanging residue with a screwdriver. This is the finished playfield. In the next step I will install the lamps and sensors, but that will be in my next video on YouTube. Thanks for watching.